So first of all, I will introduce what is Murex and what is Murex Analytics for the one who don't know us. I do it very quickly. Then I will tell you what is this thing, the IBM Minsky, and you will see that it's a computer with new features that can be interesting to finance, but also to other cases. Then I will show you a few benchmarks for the P100 that we have run, local benchmarks that we have run with the Minsky computer. Some have results that we have expected, and one has a better result than what was expected. So I will come into details of what it is better than expected, so it's interesting. Next thing I will tell you, I will go into a case where we will see that NVLink, which is the link between GPU and CPU that is featured by the P100, can be useful in finance because it's not obvious that NVLink is needed or not. Then I will come to a part which may be a bit more boring, which is the case where we do not look at a single problem in finance, but we globally look at more problems together. And we see the effect, what we need to do to make a system that has multiple GPU, that has to cover a big bunch of pricing and risk management together, works better than if we had only done the usual things. And I think that it's relatively important when we build a system to have in mind that we are not looking at single pricing or single MVA computation, but we are looking at a system. And there are some problems linked to that. And I will tell you how we tackle this problem. Then I will give you some global benchmark just to have a feeling of how Minsky is behaving relatively to previous computer. And then I will do some perspective for Volta and for the future. Okay? So first, what is Murex? So we are a big vendor of software for trading rooms. So meaning that we can clearly price and risk manage product, but we can also use our system to book the products, to look at accounting, to everything. It's like an SAP of the trading room, meaning that analytics is not the only problem we got. In fact, it represents 1% of the problem we have. And most of our competitors do not propose analytics. They leave either the banks developing them or external bundle like Murex proposing them. We do think that it is important for our system to also propose analytics because it enables us to have a far better understanding of the problem of our customer. And since also a lot of analytics are becoming standard now, it is useful to implement very optimized analytics in a system and leave the bank implement the specific analytics they have where they want to have an added value. Relatively to GPU, we are not new with GPU at Murex, something that we start in 2009, even in 2008, we had a first example of GPU programming. And we have been in production with GPU for a long time already at many customers. I don't even know the list of the customers we have now with GPUs, but it's becoming really the standard. Each time somebody wants to have at least a first generation exotic price inside Murex, it is naturally proposed to use GPU when they use our models. And clearly for XVA, it is the normal. And clearly for our customer, what it means first that they use less hardware. Because clearly, when people want to buy a system, they look at the TCO of the system, and they don't want to use too much hardware. Then it enables them to have more precision, so they can increase the number of paths in simulation, for instance, and use more complex models. So then, what is this Minsky? So there is something that I do all the time, is that I look at the HPC market, at the supercomputer market. Because from what I know that the market of Murex relatively to hardware is very small. globally, we do not drive the evolution of hardware, neither of software of NVIDIA, for instance. So what I'm looking at is always what are the next supercomputers and how they will be built in the future to begin developing the software that will be adapted to the components of this supercomputer and see if, because this component will become mainstream in the computer that you will have in your data center for finance. And it is always worth seeing if they can bring you something and begin develop early. So what happened is that the next two big American supercomputers are built jointly with NVIDIA and IBM. IBM is proposing the processor, the CPU, and NVIDIA is proposing the GPU. So the GPU will be a Volta, and the CPU will be a Power 9 processor. And there is a very specific thing, is that there is no need of PCI Express in this supercomputer. You got a link using NVLink. NVLink has been proposed by NVIDIA for about a bit more than 1 year. It is used to link several GPU together, so to exchange, so it can speed up many calculations in HPC. But it is not used inside the Intel computer to link the CPU and the GPU, meaning that if you got many data to transfer for any reason, you keep the bottleneck of the PCI Express. And this computer has far less, has far more bandwidth between CPU and GPU. So that's why it is very interesting to see if it works well and if we can use it in future usage. Okay, so first, after looking at the computer itself as why we want to test it, then does it work? So the first thing is that relatively, if you use some open source code, mainly, standard compilers, standard libraries that you use for like NumPy or whatever, you simply have to recompile. It works well. That's a very good thing, because before with IBM computer, it was more difficult to, when you had special IBM computer, it was not something that needed only recompilation. So first, it works perfectly out of the box. It's great. Now, there are still some bugs inside the library, not real bugs that are generating wrong results, but some performance bugs. For instance, we found problem in the string library, which are in Leipzig, that should be good normally, and it's still not corrected, but certainly it will arrive. The other point is that you have no OpenCL, you have only CUDA. I know that most of the people here love CUDA and always use CUDA, but we at Murex, we use OpenCL. We have this, in the past, we have decided to use OpenCL simply to stay open, to be able to change of GPU vendor, even if we are 100% NVIDIA forever. But clearly, it's still not on power computer. So what we got is that we got anyway a converter that is converting our OpenCL code to CUDA. So there are no worry for that, for having CUDA. But for people using OpenCL, which is something which has a lower level of abstraction, when you use CUDA, you may have some surprises. And the biggest surprises that people have is linked to memory allocation, because of the fact that now you have the possibility to allocate on CPU, transfer automatically on GPU, and do this type of things. CUDA is doing far more things when it allocates memory than OpenCL, meaning that if you purely port your code, you will have some performance problems. So it means that if you want to go to power from OpenCL, be careful of the memory allocation and do your own source to gain time time again. The other point is that the Power 8 Plus that we had is fast. It's a good processor, but it's not extremely fast. It could be faster. Hopefully, Power 9 will be better. But it works well. So then, what we are doing mostly at Murex when we use GPU. simply what we do is we run Monte Carlo simulation. So as explained in the previous presentation, simply it means you pick up a lot of random numbers, you generate a lot of paths of assets, and then either you do some averaging of this of a function above these assets, which are globally what you gain from a financial product, gain or loss from a financial product. It means to have a price. And the other thing that people do is that sometimes instead of simply looking at one financial product, they want to price. They look at all the assets they got in their portfolio of a certain or done with a certain counterpart, and they do some other computation looking at the future. It's the whole world of XVA we saw already this morning with Kinetica. Okay, so our Monte Carlo is also compatible with scripted payoff, because what people want to do is that they want to define new products each time they can to have flexibility. Okay, so it means that you can script your product. So our scripting language is based on Python, so which is totally open. Now, for sake of performance, everything which is linked to the diffusion or any complex calculation was programmed, was hard-coded by yourself and optimized a lot. We also do some kernel fusion inside to avoid this memory bandwidth problem that we saw in the previous presentation. The last thing which is important for us is that we have built a Monte Carlo which can be adapted to any amount of memory that has a GPU card. Meaning that the more memory you got, the faster we will be. But it can also run on small GPU. But the best thing is that also it can work on the GPU of the future when we will have more memory. And we have always the same results. So we use spatial random number in such a way that we can generate our paths in a way different from one GPU to another. Sorry?
In terms of the random paths, I assume that you use a special function, maybe stochastic equation, just for, so the path will actually be respecting the financial behavior.
Yes.
How hard it is to use, another function, another stochastic equation, because this is very interesting.
So globally, you've got behind, so you've got two things to look. So it's like a plugin function that you got inside the Monte Carlo, okay? Now you've got several problems to look at. The first type of model are simple, is that you can jump from one date to another with long jump, meaning, okay, you don't need to look at the intermediate values, okay? So there are other cases where you need to discretize, okay? And the other thing is that also when we talk about multiple assets, they are correlated. But globally, it's like a plugin. The only thing that you need to be careful is the discretization. And clearly, also in terms of, for some of the models, there are ways to speed up these jumps. For instance, models, there are some specific formulas and so on that help the model converge better at the level of the path. But it clearly, here, for each model, things are different. Okay, so then, looking at the P100, so first a benchmark, a small benchmark. In everything that I will show you today, the products are very simple. I have chosen especially to have simple product because they give me performance problem. Because when you have a very complex product with a very complex function inside, it is really GPU adapted. It is really compute bound. The more it is compute bound, the more it is GPU adapted. So what I took in this sample are always cases where globally we have some sort of equilibrium between compute. We feel the bandwidth problem, and we feel the CPU problems also. It is really decided. I decided to do so to see what needs to be done to tackle the problems. So first of all, so the product I took is something relatively simple. It is called twin-win autocall. So autocalls are products that are a lot traded on equities. Mainly, they give you a coupon every X year, or X months, I would say more. And if you die, if you go above a certain barrier, you die. And if you go, and often if you go down a certain barrier, you are transformed into something else. And if you are not dead and not transformed, at the end you've got a specific payoff. So this twin win is something that gives you at the end a straddle. Okay, but it's a product I received from the bank 1 year ago. It was traded at this time, but it's a real product. Okay, so the good thing is that it has a continuous barrier, so you need to have discretization. So it means that the Monte Carlo you see here for something which is based on Black-Scholes model, you can imagine that if you were using local volatility for the people who are from the quant side, you will have the same performance. Okay? So what we saw is that globally, so we use always a huge number of paths to show you the performance. Okay? So globally, what we saw is that we are something going from the K40 to the P100. We've got something like a factor 3 performance improvement. So I never show again CPU time. I do not test them, and certainly my code is not optimized for CPU anymore. So I won't talk about CPU itself. It won't. But the good thing is that globally, this P100 card, for simple computation, it gives you really what you expect, something which will be linked between the compute benefits and the bandwidth benefit. What is interesting also is the fact that you would maybe tell me that you as a banker will not need 16 million paths Monte Carlo to have what you want. The good thing is that with the way we have built our Monte Carlo is that these 16 million paths can be used to compute one price, but also you can split these paths and compute sensitivities at the same time. So it means that if you want to have, if you use 160,000 paths for pricing and you want to have 100 sensitivity, you can use the same Monte Carlo and the same time under the second to compute all the sensitivities at the same time. So it's a pretty good card. Another benchmark that we run is that we look at the calibration of local volatility. So in fact, if you look at this equity product, it is mostly priced either with local volatility or local volatility with jump on the market. And what is long is not to compute the price, but more to calibrate the model. And the calibration of this model is built with to calibrate this model, we need to price PDEs. So PDEs are more complex to program than Monte Carlo because they are less parallel. So during the first GTC, I missed. There was a presentation showing an old algorithm that was used when Cray created their first computer, which is called PCR. And PCR is solving a three-diagonal equation in n log n operation or in log n step for a GPU. And it's a great algorithm. But this algorithm, when we were launching it on K40, was not really faster than on M2090. And what we saw is that globally, using the P100, instead of having the factor 3 we were expecting, we have something like the factor 6 or 7 on PCR. Here again, what we do is that we do not calibrate only one case of local volatility, but we calibrate 1,000 local volatilities at the same time, which is very useful when you compute sensitivities, because clearly if you think about a basket product and you want to have all of your sensitivities to the asset, to the volatilities, to the different rates that we have, you will come to something like 200, 300 sensitivities and 300 calibration that you have to run at the same time. So here again, we arrive at a better time, and clearly we have a far better improvement than expected. So what was the reason? The reason was that in K40 there was something like a bug. Is that clearly we had far more cores than before, than we had on the M2090, but clearly we were lacking some register. So it was corrected a bit on K80. That's why the K80, often when you test the K80, you see that the K80 is faster than 2 K40, even if you use, even because you got 2 small K40 in a K80, you often see that it is faster than what was expected. The frequency is lower, but in practice, we see that a K80 is often better than 2 K40. But the reason is also linked to register. But that's a good thing that the number of register is correct at the level of the P100. And we can run the more complex code without problems. Okay? Next thing is about NVLink. Do we really need NVLink? Okay, that's the reason why we are testing this computer. So where do we transfer data between CPU and GPU? There is only one case in our world. It is at the level of the XVA. So what we did is that we took one sample of what we do during XVA. So globally, what we did is that on XVA, we compute, so we have got, for instance, 8,000 paths, 120 dates, something like that, and we price several swaps at the same time. And XVA is more linked to pricing the vanillas than pricing the more exotic product, because it's linked to what you got, the volume you got with your counterpart. And here again, we see a big improvement in performance. But what we see also is that the part we take to compute the payoff itself, the 0.266, is relatively compatible to what we see on the upper left part of the screen, which is with the time you need to transfer the data between CPU and GPU using PCI. If we were not using PCI Express, we would have exactly the same time here and here. But globally, what we see is that NVLink is giving us more space. So for CVA, it's good, but clearly it was not needed, because globally the overall time that we had was not really linked to this transfer time, even if now payoff and transfer time looks a bit the same. You can overlap both. Now, if we think about the MVA is to compute value matrix for your portfolio at each of these points. So globally, you will compute something like 100 or 100 price per node, per point of the grid. So it means that this time, you will have to transfer far more data. Now, also, since we are pricing mostly a simple vanilla during the XVA, there are ways to optimize the time to compute the sensitivity. Not everything will be computed by finite difference. If you think about a swap, clearly everything will be computed using either AD or AD. And AD will generate far less computation for each of the sensitivity than what we need for the payoff. So globally, it means that this time, when we think about MVA, it will be multiplied by 5, for instance, but not by 200. Meaning that then, this time to transfer data may be a problem. So that's the reason why we look at this NVLink that works perfectly well on the computer. So now, what do we do to think about the future? Sorry?
The last picture, top right, what was the 25G?
Top right. This Power 9, it is 25G. Honestly, I don't know. I copied that from NVLink, from the NVIDIA, but I think it's giga something. They have changed. This is their. It is in byte, I think. It's. I think it's gigabyte transfer, but I'm not sure. I should look at.
It would have to be gigabytes because it's gigabits, so it'd be.
It can normally, I think it's gigabyte, some sort of gigabyte, but it's per lane or for all the lane, I'm not sure. I think it's per lane. Normally, I think it's per lane. Then it will come to the 300 gigabyte per second they say for Volta, but I'm not sure.
I wonder if it's Mellanox or Ethernet.
No, it's not about Mellanox. It's about the bandwidth of the NVLink. Okay, but globally, I don't know which are these 25, but globally the factor you see there are the one we will have. We don't know when we will have PCI Express 4 in Intel, okay? We clearly see the difference between PCI and NVLink 1, and hopefully we will see the 70% improvement with the next computer. But I haven't tested. So now the thing is that in a system like ours, we do not have only one pricing or one grid to compute. It's globally we have many threads, many sensitivities, many XVA computation to do at the same time. So I have simplified a bit the way the computation part of our system is looking at. So it's not the exact thing that we have, and it's not the whole system. It is only the analytical service part. So globally, what happens often is that when you think about analytics, you want to have a service like a calculation server that does that. Okay? So you have also, so first, in our case, we receive some JSON documents. Now also what happens is that you want to be able to price many threads at the same time, to have several sensitivities. So you have to have to use several computers at the same time. You want to have a grid of computer. Okay? Also, you have to prepare data for models. Often what we see in benchmark is that you see, okay, this model is fast now on GPU, but you often forget that mainly for a computer, you need the input of the model are not what the traders are looking at. They are looking at the other data. They are maybe stored in other place of the system. They have to be prepared. Also, when you have a thread, the thread that you see on your screen is not the thread the model is expecting. So using scripting and so on, you need to modify the way it looks to be model compatible. So globally, in our system, what you have is that you've got two layers of grid. There is the first one, which is a Python one, that is gathering all the data necessary to do pricing and risk, and also transforming payoff into something understandable by a model using the scripting. Okay? So this part is written in Python in such a way that we can be flexible and add more and more cases. And then the other part is that you got a grid of CPU and GPU computers. Okay? And they transfer data using Ethernet and XML and JSON and so on. And you have to take that into account. So what we see is that there is one thing that we always see when we use a new GPU is that the more paths we put inside or Monte Carlo, the best is the performance. Often when you got, since you got far more cores each time for a GPU, you will, to obtain the good performance, you have to put more paths. Clearly, we can use these paths to compute sensitivities, but you use more paths. But also, it means that you need to prepare more data. And what I want to show you on this screen is something very classic that we see in many places in our software, and in most of the cases when we want to launch a VAR on simple product. Because on the VAR, for the pricing, you need less paths, because what is important is to know what is the scenario that is generating the problem, what is generating the VAR, not the precision of the price at this point. So you need less paths. And each time you need less paths, it means that you have less performance at the level of the GPU. So it means that what we do is that instead of computing one price for each point of the VAR, we compute on each of the GPU, we compute several points of the VAR at the same time. But also, we need to gather far more data. And what we see is that globally, we have a time which is increasing on the CPU grid. And we have a time which is also of treating the XML we receive for the model, which is also increasing. Meaning that we have very big difficulty to use efficiently at 100% GPU when we are inside the big system. Locally, when we develop a model, we can use very easily the full GPU, but inside the system, when you've got all the integration part inside, you've got difficulty. It doesn't mean that we have bad results. For instance, on the right part, what we see is that in 1 second, we can evaluate this something like 1,000 prices when we use a 16K pass, which is not a bad result, but it's a problem. We cannot use the GPU totally. So what we do is that now what we use, and instead of saying that we want to use it 100%, we prefer to use the same tool people are using for MPI, mainly to use the multiple process system that is provided with CUDA. It really enables you, instead of saying I want to really use this GPU 100%, what we see, it is far more, it is easier to say that we want to overload the GPU in such a way that it will look a bit slower and that the CPU will run at a bit faster relatively to him. But be careful when you want to use several processes per GPU. If you simply launch several processes directly on the GPU, they will all interfere together. So clearly, you need to use MPS. So for instance, in our case, what we find is that the usage of 4 processors using MPS is the best thing to be done at the level of Minsky. But it has to be tested.
Yeah, I understand.
Okay, I have to go. Okay, so I will finish quickly. Other thing that you have to take care with Minsky is the fact that you've got SMT. It's a tool that enables you to use several threads on the CPU. Be careful also, do not use too many threads. It's bad. 2 is best. Okay, then a benchmark. When we use only one Minsky, what we do is, for instance, we price several autocalls together. What we see is that if we use, for instance, like 16K pass, we obtain something like a throughput of 10,000 pass per second. So it's the best thing we never had. I will stop in 2 minutes. Okay, but there's nobody after me. So, okay, sorry. So then the future. So globally, Volta. If you look at the Volta design, you will see no problem with the register and so on. It should work perfectly. So you should have something like a 50% gain. Next thing. So globally, Power 9 will give us 2 more times the number of cores. So it will be great. So hopefully, next generation will bring us better result again. And we expect a factor 2 with 6 GPU and 2 Power 8. So I will tell you that next year, if it's okay. Okay, that's it. But be careful, optimize your CPU code. Okay, thank you.